Hi, this is Dane Quinn from the University of Akron, and today I'd like to give you a video lecture that really introduces mechanical vibrations. Here's the system we want to consider. I have a block of mass m that is suspended by a spring with stiffness k under the influence of gravity. And I would like to find the displacement of that block when it's released from rest at the unstretched position of the spring. So the idea is that I'll take the block and I'll move it to a point where the spring is unstretched, and then I'll let it go and I'll see what happens. Well, we kind of can guess what's going to happen, right? This thing will initially fall, and at some point it will pause, turn around, and then recover that motion. And it will actually oscillate back and forth forever, really, because in this model there's no dissipation. There's no way to dissipate energy in the system. Not the best model of a real physical system, but it's a good place to start our discussions for mechanical vibrations. So the first thing we're going to do is model this system mathematically. And then once we have that model, we will go and solve for the response. So we need to first talk about how to model the response of these kinds of systems. Well, I've really broken this procedure down into kind of 5 steps, and they're listed over here on the right. So the first step actually is just to sort of think about the problem, right? So we don't really do anything, which is why I don't number this step. It's kind of step 0. Really, all we want to do is just identify sort of what's going on and think about the motion. It's always a good idea to spend a little bit of time and think about what's going to happen before you jump into trying to model the response of a system. I will start off and identify the forces that act on this block, and I'll draw those in over here. This is not really a free body diagram because all I'm doing is just saying, hey, the forces exist. I'm not going to tell you what they are. That step comes later, really step 3 as we see here. Right now, I just want to figure out what's going on. Right? So I've got 2 forces that act on this block. Right? One is a force due to gravity. Right? So we'll call that F of gravity. And the second force that acts on the block is due to the spring. Right? So here, and we'll say that's F spring. Again, I'm not telling you what these things are. I'm just saying they exist. Now, we also want to think about the motion a little bit. Right? So the block is constrained to move in the vertical direction. Right, so we're not going to allow this block to kind of rock back and forth. Instead, it can only move up and down. Right, so it only moves in one direction, and these are the forces that act on it. Okay, so now really where we start to do the analysis is identify the coordinates that we're going to use to measure the forces as well as the motion and the associated directions. Right, so the way this works is that if we think about what we do last, the last thing we're going to do is apply the equations of motion. Well, in order to do that, we need to know something about the forces, right? So that's our free body diagram. We need to know something about the motion, that's our kinematics. Well, in order to define these 2 things, I need some coordinates and directions. Right? So that's actually what we're going to do now. And in order to figure out what coordinates and directions that we need to define, well, we need to think about what's going on. We need to identify the forces and moments, perhaps, that act on the system and describe the motion. So again, starting at the end and working backwards, this is kind of a fairly logical procedure, right? So we think about what's going on, we figure out how we're going to measure it, and then we go and calculate some things, motion, forces, and then finally we apply the equations of motion. So, jumping in, right, what forces do we need to measure? And what directions? Well, here the motion is going to be in the vertical direction, right? So we'll call that J, and we'll throw I along with it. That's the horizontal direction, and it's perpendicular to J. And now we need some coordinates. All right, well, the motion of the system is going to be naturally described in terms of, say, the position with respect to the ground, right? So we'll call that x. So when we talk about how this block is moving around, x is a natural coordinate. The forces, on the other hand, well, in specifically the force due to the spring, is given in terms of the stretch in the spring. So here, if I identify the unstretched length as L, then the stretch in the spring is, well, it can be identified with a coordinate z. Notice that I have two different coordinates, right? And the first one, right, so here, displacement of the block and if I define this point as, say, point B, B for block, O here is fixed in the ground, then the position of B with respect to O is minus x in the j direction. Right? So again, x describes the displacement of the block. Now, the force in the spring well, that's based on the stretch. And the stretch is basically the displacement of B. Right? So here, the displacement of B is minus z in the j direction. These two things are related, though. So if you look, for example, and let's define, say, a point A here that would correspond to the unstretched position of the spring. The position of B with respect to O is the position of A with respect to O plus the position of B with respect to A, right? So basically it's this vector plus that vector equals that vector. And so this position of B with respect to O we said was minus x in the j direction. Position of A with respect to O, that's minus L in the j direction. And the position of B with respect to A is minus z in the j direction. So looking at the j direction, right, we see that x is equal to L plus z. Now, you probably could have just looked at this and figured this out, but it's nice to be able to come up with these kinds of constraint relationships in a rational coordinated way. So here we have our coordinates and directions. Well, it's time to move on. And the next step now is the kinematics of the system. So here, in terms of the coordinates and directions that we defined, we want to go and write the acceleration. So the acceleration of the block is, well, it's defined as the second derivative of the position, right? So the position of B with respect to O. So that's going to be the second derivative of minus x in the j direction. So here, j is obviously constant, and so this becomes minus x double dot in the j direction. Dots indicate derivatives with respect to time. In addition, we need to figure out what the initial state is, right? So the initial conditions, well, it was released from rest at the unstretched position. That's what the problem statement said. So here, if it's unstretched, that means at time 0, z is equal to 0. And if it has no initial velocity, x dot at time 0 is equal to 0. So we have the kinematics, namely the acceleration and the initial conditions, in terms of these coordinates. Now we turn to our free body diagram, right? So here's where we actually take those forces, right? So we had these forces that we identified previously, and we define them in terms of the coordinates and directions. So this spring force is minus the stiffness times the displacement, right? So here the displacement was minus z in the j direction, right? So we can write the spring force as k times z in the j direction. Just sort of looking at this, if z is positive, that means this block is displaced down, and then the resulting force from the spring is going to be up. Right, sure enough, if z is positive, then this force is in the plus j direction. For gravity, we just have minus mg in the j direction. So now we're almost done. All we have to do is apply the equations of motion. So here we'll use linear momentum balance. And that's sum of the forces equals the mass times the acceleration of the block. So really at this point we just take everything that we've done before and we toss it into this equation. So the forces, k times z in the j direction, and minus mg in the j direction. And that's going to be equal to the mass times the acceleration, minus x double dot in the j direction. So here, taking this in the j direction, we see that k times z minus mg equals minus mx double dot. And notice that we have z and x here in terms of this equation. So because these are related, let's go ahead and eliminate one. Let's choose to write this in terms of x. Remember that x is equal to L plus z, so that z is equal to x minus L. So using my constraint equation, I can write this as mx double dot plus k times x minus L equals mg. And this becomes the equation of motion for this system. Now we turn to the response of the system. So here over on the right, I have again shown the equation of motion. Notice that I have brought all of the terms that don't depend on x over to the right-hand side, in particular the k times L. I've also transformed the initial conditions to being in terms of x alone. Now, the response is determined by solving the equation of motion and satisfying the initial conditions. So the equation of motion, which is this differential equation here, and satisfying initial conditions. And that is given in the second line. Now, in general, the way that we do this is to break up the response into two pieces. Right? So x of t is going to be the solution that we're looking for. And we'll actually construct that in two steps. Right? The first step will actually be to solve for what's known as the particular solution. And then we'll turn and solve the homogeneous solution. You know, if you've had a course in differential equations, which, you know, at this point you probably have, then you'll recognize this. The particular solution, well, that deals with the forcing. Right, so we're basically going to try to take care of this right-hand side by some solution. And then once we have that, we'll finally deal with the initial conditions through the homogeneous solution. Again, this particular solution, it just concerns the forcing, right? Any initial conditions, any solution that satisfies the forcing requirements will work as the particular solution. And then once we have that, again, we'll go back and deal with the initial conditions later. Right, so why does this work? Well, let's take this assumed form and substitute it into the equation of motion. Right, so basically, you know, the equation of motion looks like m times the second derivative of x plus k times x equals mg plus kl. So what I'll do is I'll take this assumed form and substitute it in. Right, so we have now second derivative of xp, that's the particular solution, plus xh, plus k times, again, that assumed form, equals mg plus k times L. So I'm going to collect the pieces of this that are in terms of xp, the particular solution, and the pieces that are in terms of the homogeneous solution. All right, so we'll do the following. We'll collect those particular pieces in orange. All right, so I get mxp, and I'll just use double dots now, plus k times xp. And then I'll collect the homogeneous parts. All right, so that's going to be m times xh, double dot, plus k times xh. And that's going to be equal to, well, I'm going to do the forcing in orange, right, kind of to highlight the fact that it goes along with the particular solution. And then we don't have anything left over. So really, these orange pieces will go together, and the pink pieces will go together. So if xp satisfies the following equation, m times xp double dot, k times xp equals mg plus kl, and the homogeneous solution satisfies the pink part, then clearly this equation is satisfied. Now, we also need to satisfy the initial conditions, right? So let's look at those. Here, x initially is going to be xp initially plus xh at the initial time, and that's got to be equal to L. And likewise for the initial velocity, it's the initial velocity of the particular solution plus the initial velocity of the homogeneous solution. And here, that's equal to 0. So now, remember the particular solution, any initial conditions work, right? We're just looking for some solution here. Then, the initial conditions for the corresponding homogeneous solution still have to satisfy these two in the box, right? So in particular, xh, the initial displacement of the homogeneous solution, is L minus whatever the initial displacement of the particular solution was. And likewise, the initial velocity of the homogeneous solution, well, that's going to be 0 minus whatever the initial velocity of the particular solution was. So if I can satisfy these two pieces, right, the thing in orange and then this stuff in pink, then I have a solution to this equation, right? Because I've gotten the equation and I've gotten the initial conditions down. Let's look at the particular solution first. I've rewritten it here in orange again. And remember, this is any valid solution. We don't have to worry about initial conditions. We don't have to worry about long-term behavior. We just have to find something that works. Right? So again, there is no consideration of initial conditions. And usually we want the simplest solution possible. Simple's always better. Well, almost always. The simplest solution, in fact, typically looks like the forcing itself. All right, so whatever the forcing looks like, that's probably what the particular solution looks like. So it's of the same form as the forcing. And by forcing, of course, I mean the right-hand side of this equation. So we need a solution that satisfies the equation of motion. The right-hand side, the forcing is constant, right? So let's look for a constant solution. So if the solution is constant, then the derivative, x dot, is equal to 0. And likewise, x double dot is equal to 0. So we'll substitute this into the equation of motion. And what do we get? Well, we get something that's pretty easy, right? X double dot here is 0, right? So I get m times 0. K is just a constant, and I want that to be equal to mg plus k times L. So I need to solve for C. Right? C is my unknown particular solution. Well, can I do this? Yeah, I can do this. Right? And we find that C here is equal to mg divided by k plus L. So this becomes the particular solution, right? It works. If I take this and I substitute it into the equation of motion, right, the left-hand side equals the right-hand side. Therefore, I have a solution. Now, we can talk about this a little bit, and one interesting thing to note is that for constant forcing, like we have here, the constant particular solution corresponds to static equilibrium. So if you were just to solve this as a statics problem, and you ask what's the static displacement of the block? Well, it's where the force due to gravity balances out the spring force. And solving for that, the displacement from the top is the length of the unstretched length of the spring, L, well, there it is, plus the stretch in the spring. Well, that's just going to be mg over k. Right, so again, these solutions that we find, they typically, well, they always have physical meaning, right? They have some sort of physical interpretation as to what's going on. in this case again, constant forcing, the constant particular solution that we would find corresponds to the static equilibrium position or state of the system. So here we have our particular solution. Right? In general, the particular solution is a function of time. In this case, right, it happens to be constant. Right? But of course, a constant is still a function of time. Now let's turn to the homogeneous solution. Right? So here it is again. Right? This is the homogeneous equation that we found earlier. And now we have the initial conditions that we found earlier. Well, for this system, right, for this solution that we found, the initial displacement of the homogeneous solution is L minus the initial displacement of the particular solution, which is just mg over k plus L, which actually is minus mg over k. And because the particular solution is constant, its velocity is always 0. So the initial velocity of the homogeneous solution, right, should be 0. So again, we're looking for a solution to this equation with these initial conditions. So this homogeneous solution, it solves the equation with no forcing. And must satisfy specific initial conditions. I will note that the initial conditions for the homogeneous solution are not the same as the initial conditions for the original problem, because they're the homogeneous initial conditions are the original problem minus the particular solution. Right, so this is something that we need to calculate along the way. And to solve this, right, we will use the method of undetermined coefficients. Which really means we'll assume a solution and then try to make it work. You know, I sometimes kid, this really should be called the method of really good guessing, because we have to guess a solution that works, and then if we guess a solution that works with some undetermined coefficients, then we make those coefficients what they need to be to work out. Do I expect you to know what the right solution should be ahead of time? No, but for the class of problems that we're going to deal with, right, it'll always look like a very familiar form, right? So we're going to assume a solution of the form xh, again this is the homogeneous solution, is harmonic, right? So there's an unknown A amplitude and an unknown frequency, and then a cosine piece as well. Right, so really, this A is unknown, B also unknown, and then the frequency is unknown. So we need to choose A, B, and omega so that this works. Okay, well, just like everything else we do, let's go and figure out what, well, in this case, the acceleration is, and then substitute into the equation of motion. X dot here is A omega cosine omega t minus B omega sine omega t, and the second derivative is minus A omega squared sine omega t minus B omega squared cosine omega t. Okay, we now need to substitute this into the equation of motion. And we get m times, well, this piece, minus a omega squared sine omega t. Again, omega is an unknown frequency. A and B are unknown amplitudes. And then plus k times x, so that's a sine omega t and b cosine omega t equals 0. So we'll solve this by collecting coefficients of sine and cosine. Notice that this has to be a solution for all time. So the coefficient of sine is minus ma omega squared from here plus k times a sine omega t, and then the coefficient of cosine is minus mb omega squared plus k times b equals 0. So in order for the left-hand side to be equal to 0 for all time, both of these terms in brackets have to vanish. Right? If this was non-zero, then for some time there'd be a non-zero left-hand side. Right? And there's no way to make these two things cancel out for all times unless, again, these coefficients are equal to 0. So here, the solution satisfies the equation of motion if minus ma omega squared plus k times a equals 0 and minus mb omega squared plus k times b equals 0. Notice that if I factor out an a from this equation and a b from this equation, I get exactly the same thing. Right? So in particular, these work if minus m omega squared plus k is equal to 0. So we can solve for omega. And we find that omega is the square root of k over m. This is actually defined as omega n and referred to as the natural frequency. I make this distinction because here omega was just some frequency to be determined. And now we find that frequency needs to be the square root of k over m. And because this appears so frequently, we give it its own name. And again, that's the natural frequency. Here we've solved for this frequency of oscillation, but notice that the undetermined coefficients a and b, these amplitudes, are still unknown. Those actually need to be determined to satisfy the correct initial conditions for the homogeneous solution. So here it is again. This is the equation, initial conditions, right? And the general solution, before we determine a and b, is a sine, and I'll use omega n now, and b cosine omega n t. Remember, omega n is the square root of k over m. A and b are, again, arbitrary, and we need to choose them so that these initial conditions work out. Well, how do we do that? Well, we essentially evaluate these auxiliary conditions at the right time, which in this case is t equals 0. Right? So here, notice that xh at time 0 is minus mg over k. If I take the general solution and evaluate it at time t equals 0, I have a times sine, well, t equals 0, I get sine of 0, and I have b cosine of 0. Remember that sine of 0 is equal to 0, cosine of 0 is equal to 1. So this simply reduces to b. And likewise for the velocity, well, the initial conditions tell me that the homogeneous velocity at time 0 is equal to 0. And then evaluating this expression, right, the derivative at time equals 0, I have a omega n cosine of 0, derivative of sine is omega n times cosine, minus b omega n sine of 0. Once again, this is 1, and that's equal to 0. So we just have a times omega n. Well, this is actually fairly easy to solve. B is equal to minus mg over k, and from here, a is equal to 0. In general, each of these equations may have an a and a b in it. Just so happens with an undamped system like we have here, these things split apart. Now that we've determined the general solution and the specific values for these arbitrary constants, we can go and calculate the response of the system. Right, so looking back, that is going to be a combination of the particular solution and the homogeneous solution. So what we saw previously was the particular solution was mg over k plus L plus, now minus mg over k times cosine omega n t. Right? So again, this is the particular solution, right, from before, and this is the homogeneous solution given above. So notice that we can actually combine some of these things, and we can rewrite this as mg over k times, well, here we have 1 minus cosine, and let's go ahead and write the natural frequency as the square root of k over m times t, and then plus L. So if I look at this response, we have a constant offset of L, and again, remember that was the unstretched length of the spring. And then we have some other piece, right, that scales with the static displacement. A little more detail, right? We can go and, again, here's the system that we're looking at. We can plot this response as a function of time. So here I've plotted the displacement as x positive down, right? Remember, if x is greater than 0, then the block is displaced down, right? So again, I'll plot x positive down. And this dark blue line is essentially the response, right? And here I've chosen some different values for m and g and k and L, and it's not important. What's important is just the general picture, right? So as time goes on, we see that the response oscillates, right? So here, this is the unstretched length. This is the initial displacement, right? We let it go, and the mass begins to fall. So here I'm sort of illustrating this mass at various times. This time is shown here on the left, and then it undergoes one complete oscillation after one full period of cosine, right? So that's t is 2 pi divided by the frequency, omega n, or 2 pi square root of m divided by square root of k. So that's the period of the oscillations. And again, that just repeats forever. Right? So the block oscillates between the upper limit, which turns out to be the initial displacement, so that's x equals L, and this lower limit. Well, here, this amplitude is mg over k, and the total displacement here is twice that. Right? This distance is L. Right, so again, this block will oscillate between L and L plus twice the static displacement. Right, so another way to think about this is we let it go. This block falls to the static displacement and then falls an equal amount below that before turning around and oscillating back up and then back down. If we added damping, these oscillations would eventually decrease and the system would approach static equilibrium as time got large. Right? But again, here we've neglected dissipation and damping in the system. Right? So these things will continue on forever. So that's our quick introduction to mechanical vibrations. Right? And in a nutshell, this is what we'll be doing this semester. Right? So if I kind of go back and look and see what we did, right? You know, we started off with a system. We went through our process to develop the equations of motion. And so that's the modeling phase of it, really taking from our undergraduate dynamics class. And then we looked at the response, right? So now this is diffie-Qs, right? We want to take this equation and solve and see what happens, right? So we go through particular homogeneous solution, we form the general solution, and then we can analyze what happens. So again, that's kind of this class in a nutshell. We'll be doing this for lots of different kinds of problems, different degrees of freedom, all sorts of things. But fundamentally, that's what this class is about. So that's it for today. Thanks a lot. I will talk to you soon.